All right, let's look at a sample projectile motion problem. I'm going to work through a couple of different examples. These are going to be examples centered around some clips that I'll show you. But you'll also need to look at the homework and look at the old exam questions, because these projectile motion problems can vary just slightly, and it can change the way that you work through them. So you'll really need to look at the homework problems and then also look at some of the old test questions to get samples of what you might be expected to do. But I'm just going to work through a couple of common examples. This first one is from Gone in 60 Seconds. Y'all might have seen this movie. It was with Nicolas Cage, and I don't know, something about his brother was kidnapped, and he had to steal a certain number of cars within one night in order to save his brother or whatever. I don't really remember. But this is a really good scene at the end when he is trying to escape from the cops, and he comes up to this traffic jam. And of course, you know, as often happens in the traffic jam, there's this really convenient ramp that allows him to jump over these police cars and what have you. We want to know a couple of things about this. We want to know what is his range. That is, you know, what is his x distance? What distance does he travel in the x direction? And of course, that we'll also need to know what is his time that he's in the air. And we'll also want to know, or we might just want to find out, what is his maximum height that he goes to. Let's go ahead and watch the clip. And as you watch the clip, I want you to think about what's the information that you can gather from the clip. Two pieces of information. Two pieces of information. So once you go and watch the clip, you can watch it by clicking here, and you'll watch the whole thing. All right, so there were two pieces of information that were given in the clip. One is his initial velocity. And we find that his initial velocity is right around 100 miles an hour. Just before he hits the ramp, he is about 100 miles an hour. So let's go ahead and convert this to meters per second. We know that in 1 mile, there are 1609 meters. And then also in 1 hour, there are 3,600 seconds. And so 100 miles an hour is about 45 meters per second. So next time you're out driving at 100 miles an hour, you can look over and tell your friend, hey, I'm driving at 45 meters per second. And they will no doubt be impressed. Another thing that we need to know is that, well, let's just treat this as our ramp. You know, this car is going off of this ramp. We know what his initial velocity is, but we also need to know, what is this angle theta? What do you think that angle theta is? Well, you know, I think that the angle is probably the angle that would give you maximum range, because I want to make this look as impressive as possible. So let's just say then that theta is equal to 45 degrees. And then we'll see if that range seems reasonable as compared to what it appears to be in the video. But it might not be quite 45 degrees, but I think it's almost 45 degrees. And that's going to give us the upper limit for our range. Now we can calculate the components of our initial velocity. That is, we can calculate what is the x component of the initial velocity, and we can calculate the y component of the initial velocity. So I'll call these v0 x and v0 y. Just remember, graphically, I'm looking at it like this. This is my vector v0. This is my vector v0 x. And this is my vector v0 y. And this is my angle theta. That should look really familiar to you, because we're dealing in vectors now. We just want to find the x and y components. So as we've already done, this is going to be v0 cosine theta. It's going to be 45 meters per second. It's cosine of 45. Let's see, that's equal to 32. And then for the y component, since the angle is measured off the x-axis, it's going to be v0 sine theta. And that's 45. Excuse me, sorry. Deleted page, there we go. Okay, so 45 cosine of 45 which is also equal to 32 meters per second. When your angle is 45 degrees, your x and y components are equal. So there's my x and y components. Now, if I were to plot out this trajectory, it's a pretty simple projectile motion problem. Piece begins and ends at the same place, though you have some problems in the homework where that's not the case, where you're ending at a different place from where you're starting, a different height from where you're starting. I know that the velocity in the x direction is constant, but that the velocity in the y direction varies, and that at the top, the velocity in the y direction is equal to 0 meters per second. It's just like we saw in the last chapter. So I can use that to find the total time. I also know that the time at the top is equal to 1/2 the total time, because it is symmetrical, this motion. That it begins and ends at the same point, so half the time is required to get to the top, and then that same time to get back down to the bottom. All right, so begin with my kinematics equation. And notice now that whenever I use these kinematics equations, I'm always putting a y or an x, because I need to know which dimension I'm talking about. And I'm going to call this t top. That's the time at the top. And so this is going to be 0. V0 y was 32 meters per second, minus 9.8. If I solve for t top, that's negative 32 over negative 9.8. I get 3.3 seconds. Right. So that is the time up here. That means that the total time, that is the time down here, is going to be twice that, or 6.6 seconds. So that's one of the things that we want to know. And in fact, if we find the range, then we'll need to use that time. So let's go on down. So the total time in the air is 6.6 seconds. And if you look at the clip, you can go back. You find that it's about 7 seconds. So that's not completely absurd. And it also lends some credence to our assumption that the angle is 45 degrees, because 45 degrees will give you maximum time in the air, and any other angle will give you less time in the air. All right, so next we can find the range. Well, let's find the horizontal range. X is going to equal V0 t, that's V0 xt, plus 1/2 at squared. This is axt. And just to remind you, we're looking for this distance, x. The acceleration in the x direction for projectile motion is always equal to 0. And so we have 32 meters per second times 6.6 seconds. And that gives me 211 meters. That seems a little high to me from what we see in the clip, but it's not absurdly high. I could envision maybe 200 meters, maybe more like 100, 150. But, you know, it's just a movie. So that's our range. Let's go ahead and find out now. I don't ask this, but let's go ahead and find out what is y. What is the maximum height? I'll do this over here to the side, and then I have one more question. But while we're talking about range, I say y equals V0 t, V0 yt, plus 1/2 at squared. Now remember, which t am I going to use? Am I going to use the 6.6 seconds? No, because that would be the position, the y position down here. In fact, if I put in 6.6 seconds, I would find that the y is equal to 0, because that's what it equals down here. So I'm going to put in my t top. It's going to be 32 meters per second times 3.3, excuse me, 3.3 seconds plus 1/2 of minus 9.8, 3.3 squared. All right, let's see. That's 106. Actually, keeping proper sig figs, 110 plus, or rather minus 53. And I get 57 meters. Again, maybe a little high, but not absurd. All right, so that's my y range, is 57 meters. And I also want to know, what is the speed at impact? Well, that should be an easy problem, right? If we're assuming no air resistance, it should be fairly simple to find the speed at impact. You can go through the calculations, but you'll find, that Vx, that at least for Vx, that the acceleration in the x direction is equal to 0. So this term goes away. And so Vx is equal to V naught x, which is 32 meters per second. And then we'll find that Vy, which is going to be V naught y plus Ayt. If you put in these values, that is 32 meters per second minus 9.8 times 6.6 seconds, then you'll find that this is also equal to negative 32 meters per second, because it's going to have the same y velocity as it had when it first took off. So his speed at impact is just going to be 100 miles an hour. So his V final, his speed, that's the magnitude of this vector, is going to be 100 miles an hour, or 45 meters per second. That's assuming, of course, no air resistance. All right, that's a good example. There are a couple of quick tests. You'll have to do these on your quiz. I'll leave those for you. And then, as I said, there are other examples in the homework that you'll need to work through, and then also other examples in the old exams. We'll do one more, and then we'll be done with this chapter. I'll pick up with this in just a while.